Hello, this is Talha Kemal Koçak. I'm a master's student in Gazi University, Department of Environmental Sciences. In this study, we investigated ambient volatile organic compounds in two crude oil production plants to determine their characteristics, ozone formation potentials, and health risks associated with the exposure. Volatile organic compounds, VOCs in short, are a large group of hydrocarbons that have low water solubility and high vapor pressure. There are more than 200 VOC species. Some examples include benzene, toluene, ethylbenzene, and xylens, collectively known as BTEX. Exposure to VOCs has been reported to cause several negative health outcomes, including birth defects, heart conditions, respiratory system disorders, dizziness, and headaches. Moreover, certain VOCs, such as benzene, has been classified as human carcinogens by the International Agency for Research on Cancer. Additionally, VOCs can react with OH radicals in the presence of UV radiation and nitrogen oxides, contributing to the formation of tropospheric ozone. The oil industry is a significant source of VOCs. Therefore, there are several studies focusing on VOCs in refineries, petrochemical complexes, and gas stations. VOCs in crude oil production plants, however, has been rarely studied. In crude oil production plants, crude oil is collected from wells, separated from water, and temporarily stored before transferring to a refinery. These plants are big parts in the oil industry, and their impacts on air quality and workers' health should be understood. To address this issue, we investigated benzene, toluene, ethylbenzene, xylens, and 1,3,5,3-methylbenzene in two crude oil production plants in Turkey. Specifically, we determined their characteristics, ozone formation potentials, and health risks associated with the inhalation. Methods. These are the study areas. Ale plant is shown on the left of the screen, located in Diyarbakır province, and Nusaybin plant on the right, located in Mardin province. In the plants, there are several oil storage tanks, a couple of heater treaters, and separation units. There are also tank track activities inside the plants. VOCs were collected at 8 sampling points in each plant, using passive sampling methods for 2 months in the year 2023. The red dots on the map are sampling points. After the sampling period ended, samples were analyzed by a gas chromatography equipped with a flame ionization detector and a thermal desorption system. In order to calculate ozone formation potential of a VOC species, measured concentration of that species multiplied by the corresponding maximum incremental reactivity. To calculate incremental lifetime cancer risks, measured benzene concentrations were multiplied by unit risks, exposure time, exposure frequency, and exposure duration. The result then divided by the life expectancy. Similarly, to calculate non-cancer health risks, concentrations of a VOC species were multiplied by exposure time and exposure frequency. The results then divided by the inhalation reference concentration of that VOC species. The total health index is the sum of health indexes of each VOC species. Results and discussion. The concentrations of total 6 VOCs varied from 5 to 89 microgram per cubic meter in the Nusaybin plant and from 8 to 155 microgram per cubic meter in the Ale plant. Toluene and xylens were the most dominant VOC species in both plants. These results are comparable to the findings from some other industrial regions, fuel stations, refineries, and tank farms around the world. Diagnostic ratios were used to estimate possible VOC sources in this study. These ratios involve comparing the concentrations of specific VOC pairs to infer the likely sources of the pollutants. For example, if the toluene-benzene ratio is between 2 and 3, it suggests that vehicle emissions are the dominant sources of the VOC. A ratio higher than 3 indicates a mixture of vehicular emissions and industrial activities as the potential source of VOCs in the area. In this study, toluene-benzene ratio and MP-xylene ethylbenzene ratio were used. Accordingly, VOCs in the Nusaybin plant mainly came from crude oil-related activities, while the VOCs in the Ale plant were caused by the mixture of crude oil and vehicle activities. Ozone formation potentials. In Nusaybin plant, 1,3,5,3-methylbenzene and toluene were the highest contributors to ozone formation. These were followed by MP-xylene, O-xylene, ethylbenzene, and benzene. In Ale plant, however, the contribution of toluene was the highest, followed by MP-xylene and 1,3,5,3-methylbenzene. This order of highest to lowest contribution was consistent with those reported for several suburban areas around the world. Cancer risks associated with exposure to benzene in both plants was at a possible risk level based on the incremental lifetime cancer risk classification. Regarding non-cancer health risks, they were below the negligible risk threshold in the Nusaybin plant, but slightly above the negligible risk threshold in the Ale plant. Conclusion. To sum up, we studied ambient VOCs at 2 crude oil production plants to extend the current knowledge. Regarding potential VOC sources, VOCs mainly originated from both crude oil tanks and mobile vehicles. Toluene and xylene were predominant species in both plants. Potential health risks were present due to the work exposure. This study provides detailed VOC data and analysis for crude oil production plants and emphasizes the importance of monitoring VOC levels, assessing health risks, implementing appropriate control measures to safeguard the health and well-being of workers. The results of this study also encourage the development of effective emission mitigation strategies and policies for such industrial settings. Thank you for listening.